So it's chapter 4, consumer choice. Let's enlarge the screen. I don't know. Okay. Okay, it finally. So consumer choice, and this is the book James Brander's, Jeffrey Perloff. So managerial economics and strategy. Table of contents, consumer preferences, utility, the budget, constraint, consumer choice, deriving demand curves, and behavioral economics. So we have a question here. How can a manager use consumer theory to optimally compensate employees who are transferred to other cities? Solution. So managers can assess the items employees consume in the original location and entice them to relocate by offering a compensation that allows them to consume basically the same in the new location. However, these packages usually overcompensate employees. To avoid costly overcompensation, managers may use the theory of consumer choice. Empirical method. So individual preferences determine the satisfaction people derive from the goods and services they consume. Consumers have constraints or limits on their choices, particularly their budget limits how much they can buy. Okay. Now, you may see that certain types of jobs have a much higher, let's say, compensation as compared to others. Relocation, yes, can be a problem and it can generate much higher costs for manager. For example, if you are relocated on an oil platform on the North Sea or in the Arctic area where you are, let's say, stranded from other areas, other big cities. Of course, employees working there have much higher wages. Risk is higher. You live there isolated from your family, from your friends, so it's kind of difficult. Uh, if you search one of the most dangerous jobs in the world is fishing in the Arctic Sea, in the Barents Sea, and so on. So those people also can receive high wages, or relocating you to in a stranded area in Alaska to working conditions are difficult, it's cold, you're isolated, and so on. Then we go to empirical methods. What this refers to the fact that consumer wants to maximize its utility function. We see utility depends. What depends, and considering we have a budget constraint, so we earn only a limited amount of money. Let's put somebody here on mute. Yes, I have muted somebody because some background noise. Okay, so let's share again. Okay, fine. So, consumer preference. A consumer faces choices involving many goods and must allocate his or her available budget to buy a bundle of goods. Would ice cream or cake make a better dessert? Is it better to rent a larger apartment or to rent a single room and use the savings to pay for concerts? How do consumers choose the bundles of goods they buy? One possibility is that consumers behave randomly and blindly choose one good or another without any thought. Another is that they make systematic choices. To explain consumer behavior, economists assume that consumers have a set of tastes or preferences that they use to guide them in choosing between goods. These tastes differ substantially among individuals. For example, 3 out of 4 European men prefer colored underwear, while 3 out of 4 American men prefer white underwear. Yes, so consumer preference is crucial for a market. So that's why when you decide to launch a product in a certain market, you must be aware of the consumer preference. For example, Coca-Cola may sell very well in Europe, but may not sell very well in Asia because there are other similar drinks, let's say, that may have a higher popularity. Or they may not sell, Coca-Cola may not sell well in certain countries where people have a healthier way of living, and so on. The examples can continue. Completeness. When a consumer faces a choice between any two bundles of goods, only one of the following is true. The consumer might prefer the first bundle of the second, or the second bundle of the first, or be indifferent between the two bundles. Indifference is allowed, but indecision is not. Transitivity. If A is strictly preferred to B and B is strictly preferred to C, it follows that A must be strictly preferred to C. Transitivity applies also to weak preference and indifference relationships. More is better. All else being the same, more of a good is better than less. This is a non-satiation property. Preference map is a complete set of indifference curves that summarize a consumer's taste. An indifference curve is a set of all bundles of goods. We'll see this chart. So bundles of indifferent curves further from the origin are preferred to those of indifference curves closer to the origin. Indifference curves cannot slope. Indifferent curves slope downward. So consumer preference, bundles of pizzas and burritos that Lisa might consume. So burritos per se and pizzas per semester. And we have this curve. Willingness to substitute between goods. Now we start to talk about another concept, the marginal rate of substitution is the rate at which a consumer can substitute one good for another while remaining on the same indifference curve. So, in other words, delta B is the number of burritos Lisa will give up to get, let's say, delta Z more pizzas while staying on the same indifference curves, or in other words, having the same utility function. The indifference curves are convex or bowed in toward the origin. This willingness to trade fewer burritos for one more pizza reflects a diminishing marginal rate of substitution. Now, in this course, you'll see a lot of theoretic concepts. This is this is rather advanced macroeconomic theory, or not rather, it's introduction towards medium level microeconomics, and however, we try to extract, let's say, the information that you will use as a manager in your daily decision, because when you're talking about business plan, you won't use the, let's say, the marginal rate of substitution, for example, but you will use, let's say, some statistic forecast or some models or some optimization, let's say, ways that we will learn in this course. Curvature of indifference curves. Convex indifference curves reflect imperfect substitutes. Straight line indifferences curves reflect perfect substitute goods that are essentially equivalent for the consumer. Right angle indifference curves reflect perfect components. Goods consumed only in a fixed proportions. So marginal rate of indifference curve convex to the origin, convex, so it's pointed towards the origin. Difference concave to the origin, so this is concave, this is convex. Now, in mathematics, if you have some field, the convexity and concavity has certain definitions related to derivative calculus. We'll see this later in our course. Perfect substitutes, perfect complements, imperfects also. Perfect substitutes, we see Coke, cans per Pepsi, cans per, so we have those straight lines. So what means, so if I can consume 1 can per Coke, I may substitute for 1 can of Pepsi, 2 cans of Coke, 2 cans of Pepsi, and so on to read this chart. Perfect complement, either I drink, either I consume ice cream, either pie, so I don't have to ice cream or pie. Imperfect substitutes, I may consume a higher quantity of one product as compared to us. So you see this red line, it's kind of between the perfect substitutes and perfect complements. Utility functions, we just started to. So our consumer behavior model assumes that consumers can compare bundles of goods and take the one with the greatest satisfaction. Now, in macroeconomics, you'll see that one of the main ideas is that companies want to maximize profit while consumers want to maximize an utility function, and governments and central banks want to minimize a loss related to a quadratic function If we knew the utility function, the relation between utility measures and every possible bundle of goods, we could summarize the information in difference maps succinctly. Utility functions do not exist in any fundamental sense. If you asked your mother what her utility function is, she would be puzzled, but she can easily answer. Do you want one scoop of ice cream with 2 pieces of cake, or 2 scoops of ice cream with 1 piece of cake? Or she may not know how much more she prefers one bundle to another. Ordinal utility, if we know only a consumer's relative rankings of bundles. Cardinal utility, if we know absolute numerical comparison. Most of our discussion of consumer choice holds if utility has only one ordinal properties. Now let's write what I was just saying, because okay, stop share. Now I'll go to Facebook, because we have to remember something from those let's say theories. So I'll search my groups. June, July, DBM. Oh, okay. So according to microeconomics, consumers want to maximize their utility functions, while companies maximize their profit. So this is their goal. Consumer maximize their utility functions to remember the first, let's say, significant item. Let's go to slide 12. Marginal utility is the slope of the utility function as we hold the quantity of the so Lisa's marginal utility for increasing her consumption of pizza from 4 to 5 is delta utility divided by delta quantity, so it's 20. Marginal rate of substitution, or MRS depends on the negative of the ratio of the marginal utility of one good to the marginal utility of another good. So we have those charts here. This is the budget line, or known as a budget constraint. Why? Because we have let's say we don't have an infinite revenue. We have a finite one. For example, our wage, let's say $500 a month or 400. This is our budget constraint. Effects of a price change on the opportunity set. If the price of pizza doubles but the price of burritos is unchanged, the budget line swings towards the origin. The new budget line is steeper and lies inside the original one. Unless Lisa only wants to eat burritos, she is unambiguously worse off. She can no longer afford the combination pizza and burritos in the shaded loss line. If the consumer's income increases, the consumer can buy more of all goods. a change in income affects only the position and not the slope of the budget line. If Lisa's income increases and relative price don't change, her budget line shifts outward away from the origin and is parallel to the original constraint. So these are some theoretic let's say situation. So constraint managers induce consumers to buy more units with promotions. The two most used are buy one, get one free, and buy one, get the second at a half price. The buy one, get one free promotions creates a link in the budget line, and its acceptance depends on the shape. So with the promotion buy 3 nights, get the 4th free, the new budget line is L square for both Angela and Betty. Let's say figure 420, so we can see the charts with this. So this type of promotion, buy one, get one free, does not work with all consumers. A half price promotion may be more effective than buy one, get one free if a manager can design a promotion such that consumers in different curves must cross the new budget line. Deriving demand curve. So let's go now to behavioral economics. So far, we have assumed that consumers are rational, maximizing their utility functions. Behavioral economics adds insight from psychology and empirical research on human cognitive and emotional biases to the rational economic model to better predict economic decision making. If we discuss the applications of behavioral economics, tests if the transitivity, endowment, and salience. Now let's provide an example on this behavior economics. Example of consumer psychology. Let's say average annual wage increases by 10%, while annual inflation is 13%. This is, let's call it scenario 1. And scenario 2, annual average wage increases by 1% and annual inflation is 0.5%. And the question is, which of the following situations is which of the following situation does private individual choose? Well, if we take a look at this situation, the first from a psychological point, so according to my from a psychological point, he would choose scenario one. So according to psychology, let's say economic, let's say like, with no economic background, the individual would choose scenario one because wage goes up by a higher rate as compared to scenario the second scenario. However, if we use let's say if we use our rational behavior and economic behavior and economic calculus, we would choose the second scenario. Why? Because in the first case, real wage evolution is negative, approximately, let's say 10% minus 13%, let's say minus 3%. Real wage in the second scenario is 1% minus 0.5%, so it's 0.5%. So in the second case, 0.5% is higher than minus 3%. So the second scenario is chosen. So this example shows us that we shouldn't always look at the nominal evolution. We should also analyze the, let's say, market conditions, what is happening with other variables and so on, in order to take, let's say, a rational choice and so on. Now let's share screen again. So we started with so endowment effects. People place a higher value on a good if they own it than they do if they are considering buying it. One implication of the endowment effect is that consumers' behavior may differ depending on how a choice is posted. Salience: people are more likely to consider information if it is presented in a way that grabs their attention, or if it takes relatively little thought or calculation to understand. If tax requires calculations, buyer may just ignore it because of costly bounded rationality. Now, those sophisticated calculations you have on the internet nowadays, plenty of simulators, even on banks, loans, and so on, where you just enter amounts and you are automatically provided some results. So from a certain way, this issue is solved. However, not all consumers are aware of this, or they don't want to, let's say, spend some time doing this. How can a manager use consumer theory to optimally compensate employees who are transferred to other cities? Managers collect information about the cost of living in various cities. They know that it is more expensive to buy the same bundle of goods in one city than another, and that relative prices differ across cities. Typically, relocate. Alex's firm wants to transfer him from Seattle to London, where he'll have different price and cost of. Alex spends his money on housing, entertainment, and gets a bundle S that maximizes his satisfaction in Seattle. The firm offers him enough money to buy bundle S in London. Alex may be better off. Entertainment is relatively cheap in London, but Alex is paid enough to buy bundles, so he can substitute housing with entertainment and reach a higher set difference curve. The firm may offer him less income. There is a lower budget constraint that can put Alex in London at the same indifference curves as in Seattle with less income than the previous solution. Now, this example, I don't think it's the better, because nobody wants to go anywhere with a lower wage, unless you are forced to, unless there are, let's say, worse market conditions, there's a crisis, wages drop, and so on. Certain way the conditions make you have a lower wage. Not to say about friends in a city, family, and so on. So relocation means no, let's say, at least for here, no social interaction, at least for a period. So up or slow, so those are the curves. Now let's make some exercises with this topic, and start some exercises with this topic. Okay, no. Let's see if I can find those. Okay. Okay, consumer theory just found the file. Let's share my screen now. So we have, we start with this consumer theory. So we have this utility function U, which has different quantities. Quantities can be real numbers, and this utility function also has real positive numbers. This means Rn plus, with values in R. We define the Hessian matrix, the derivatives of a matrix with the derivatives of the utility function related with different combination of quantities. Those are the partial derivatives. So, as I mentioned earlier, The goal of consumer is to maximize utility. Utility is made up of quantity 1, 2, and to n. Let's say we take the general situation, consumes n types of goods, and consider a budget of the prices multiplied by quantity. The price of each good multiplied by the quantity of each is less than equal with its wage, with its revenue. And this is a maths problem. How do we solve it? So maximize utility function, considering we have some budget constraint. The first is to construct, let's say, to implement the Lagrangian function. L, the Lagrangian function, is the utility function which depends on n quantities, quantity 1, quantity 2, quantity n, minus lambda multiplied by the budget constraint. This is the sum of price multiplied by minus revenue. So after we have shown which is the Lagrangian function, next step is to maximize the Lagrangian function. So it's quantity 1, quantity n lambda. We calculate the derivatives of the Lagrangian related to quantity 1, quantity 2, quantity n and lambda. So max optimization in many cases means that the derivative of the function related to a certain variable must be 0. So that's what we are just calculating the derivative of the Lagrangian related with each of the quantities. Quantity 1, quantity 2, quantity n, and lambda. Now the derivative of utility function. So to calculate the derivative, so is the derivative of utility related to quantity 1, because what is this derivative? This derivative means what happens if we change, what happens to this function we change quantity 1, if there's a change in quantity 1, all others being constant, remaining the same, quantity 2, quantity 3, quantity n. Minus lambda, so the derivatives, any constant multiplied by function, so constant is in front and remains the same by price, because price 1 minus revenue, the derivative of revenue related to quantity is 0, because revenue is assumed constant, and so on. Now we divide the derivative of utility related to quantities divided by price 1 is lambda. Okay. So we get to this, considering the budget constraint, the sum of all of those. And so we obtain the so-called Marshallian demand function. So the optimal, those Marshallian demand functions show the optimal quantity. So whenever we see the stars, means that we have the optimal quantity. It's a function of, so this optimal quantity is a function of price 1, price 2, price 2, and V, which is revenue. The second optimal quantity is it's a function that depends on price 1, price 2, price n, and revenue, and so on. Now, let's also write on Facebook, because to better understand this, we have to remember some derivatives calculus. Derivatives, we write them as with this sign, or df dx, sorry, which means the derivative of function f related to variable x. We assume f is a function of x, or we find fx. Okay. Okay, now let's post this one. So the derivative of so the derivative of a constant is 0. Why? Because so c is 0, because constants never change. Fx is equal, let's say, assume a function fx is equal with x. The derivative of fx related to x, so f is 1. Why? Because x, the derivative of x related to the same variable, is 1. Constant, so c is, I said c is a constant. C is a constant. C is a constant. C multiplied by x, and everything is derivative. You get the derivative. So it's constant, as we see from the lambda case. We see earlier in the lambda case, constant comes in front of the function multiplied by the derivative. So it's constant multiplied by 1 is constant. Okay. X squared, x squared, the derivative of x squared is 2 multiplied by x at 2 minus 1, and this means 2x. A general rule, x at n, derivative is n multiplied by x at n minus 1. Why I'm just doing here? Because we will the next let's say part of the course is heavily focused on derivatives calculus, and if we don't remember or don't know the rules, it will be very hard to understand at a certain level. Let's say fg are two functions. F multiplied by g, and this is it's f, the derivative of f function multiplied by g plus f multiplied by the derivative of g. Okay, at the same, we can calculate f multiplied f divided by g and the derivative, which is the same as f multiplied by minus g. No, sorry, multiplied by g at minus 1. And we calculate the derivative here. This is, if I remember well, the formula is the derivative of fg minus, minus g f derivative divided by g squared. This is another formula. Now, there can be a function, let's say f x and y. So this means that f is a function that depends on two variables, x and y. df divided by dx dy. This means that first we calculate the derivative of function related to x, and then we calculate the derivative of this function related to y. And there is a property that this is equal with dy dx. You have to check this one. Let's take a small example. Let's say we have a function fxy is x squared plus 2xy plus y squared. df dx. So the derivative of f function related to x means x varies while y remains constant. So it's 2x because we know the formula x at end, the derivative, plus 2y because the derivative of y is constant. So the constant comes in front. The derivative of x related to itself is 1. So this is y multiplied by 1. We can say plus 0 because this is so this is 2x plus 2y. The derivative of fx related to y is 0 because this assumes plus 2x plus 2y. Now we calculate the derivative of f related to this is partial derivative name because we calculate derivatives of each or part of the variables. This is 2x plus 2y, and we have to calculate the derivative related to y now. This is 0 plus 2, so this is 2. So this is so just a reminder about those formulas because we will have to handle them. Now we go back to our let's say finance related topic, consumer theory share. So we explained the Marshall. Now it's far easier for you to understand what is happening here. The derivative of u function q1. Now we don't have x here, we have the u function. Instead of x1, x2, we have q1, q2, qn. quantities, and so on. Maximum utility. So the utility in, let's say, optimal quantities, Q1 star, so star means optimal. Q2 star and so on, Qn is the utility of those functions. The elasticity of a function, the elasticity of function fy related to xg, so is this the change of function f divided by the change of x divided by fe xg. Then we have the marginal rate of substitution. We just started to present it in this current course. So we have it, the changing quantity is GA divided by the changing quantity E. So it's equal with minus the change U divided by quantity E and so on. So it's the change in the derivatives of quantities. Proof. We write the following, the difference equation. So the difference of quantity 1, quantity 2, quantity n is the change, is the derivative of utility function related to quantity 1 difference of q1 plus the derivative of quantity of u, the derivative of utility, so related to quantity 2 dq1. That q means a change, a small change in quantity. Now, I said here the marginal rate of substitution of QE, QG, all others are assumed constants, so only QE, QG remain, and the others are zero because we are assumed, and the difference of utility is zero. So the marginal rate of substitution, if we look at the definition, means how much should we change the quantity in one product if we consume more of another product. However, we keep the total utility constant. So we write this quantity of the ratio of quantities of the derivative of utility related to quantity divided by the derivative of utility of quantity G. Okay. The economic interpretation of lambda, we saw it here. Now we have it here. So if we change those quantities, lambda is the, so it's also a marginal rate of substitution here. We see that this lambda is a marginal rate of substitution utility with revenue. So how much utility changes if we a certain level of revenue changes. So even this lambda lambda has an economic interpretation. Lambda from Lagrangian function. So to implement the Lagrangian function, we have to introduce this parameter called lambda. Now this was theory, so the first part of the course is, so we presented some theoretic concepts, some maths formulas on consumer theory. We gradually introduced the concept of utility function, what is a Hessian matrix, a matrix of partial derivatives, partial derivative of utility function, the Lagrangian function, and Marshallian demand function, the elasticity function, the major rate of substitution. Now let's take an example. Types of utility function. We have the Cobb-Douglas utility. We have two variables, quantity 1, quantity 2. We have this Cobb-Douglas function is quantity 1 at alpha multiplied by quantity 2 at beta, and we will see that there are also certain constraints on those alphas and betas. Then we have the constant elasticity of substitution, or it's known as CES function, first mentioned by Arrow, Chenry, Minhas, and Solo, with A plus 1 is equal to 1. It's A multiplied by quantity 1 at minus alpha plus B multiplied by quantity 2 at minus alpha, and everything at minus 1 divided by alpha. And we have the Bernoulli, named from the famous mathematician, utility function C at 1 minus alpha divided by 1 minus alpha, if alpha is not 1. And the utility of quantity C is nature logarithm of C quantity. Then we have the Hicksian demand function. The Hicksian demand is, this time we minimize revenue for a given level of utility. So utility is equal or higher than a given level, a provided level. So this is the other way around, the other ways compared to Marshallian, in that we maximize the utility for a given level of revenue. Now we minimize revenue for a given level of utility. Now, we sometimes hear that we have to maximize utility and to minimize revenue. No, this is not correct, because we don't have a constraint. If we just have to let's say optimization conditions without having a constraint, this is nonsense. So we have the Hicksian demand function, so minimize revenue consider that utility is higher or equal than a certain level. L, the Lagrange, the first step to this optimization problem is to implement, to construct the Lagrangian function, which is the sum of price E multiplied by QE, so price 1 Q1, so minus lambda multiplied by the utility function minus average utility, let's name this. Then the next step is the condition that the derivative of the Lagrangian function related to the quantities, each of the values is 0. So this is optimizations. So price 1, because if we derive to quantity, price is constant, so price 1 minus lambda multiplied by the derivative of utility related to quantity 1 is 0. And this one, so if we derive those utilities, they are 1 minus lambda. We see that all of them are 1 divided by lambda. And we obtain the so Hicksian functions, which are functions of prices and the average utility. Q1 star. Star, as I told you earlier, means a kilogram level. Q2 star, which is the second equilibrium level, is H2, the second Hicksian function, which is a function of price 1, price 2, price n. So we explained the consumer choice problem in either of the two, using Marshallian functions or Hicksian functions, which is trying to optimize or or solve the same problem but in different ways. Exercise 1, we have the following utility function. Let's say we have a Cobb-Douglas utility function. The utility is a function of quantity 1, quantity 2. And we have quantity 1 at alpha multiplied by quantity 2 at 1 minus alpha. Considering the budget constraint. So the sum of price C multiplied by quantity E is equal to revenue. What's the first step? The first step is to write the proof that this is a utility function, because not all functions are utility function. The first derivative, so the derivative of utility related to quantities have always to be positive. This means utility is an increasing function. The more quantity we consume, the higher the utility. This is the economic interpretation of this derivative. The derivative of u related to quantities higher or equal than 0. So alpha, so when we derive, we assume Q1 is variable. The second Q2 is constant, so Q2 at 1 minus alpha is constant. So it's alpha Q1 alpha minus 1. This is positive because alpha is positive, quantities are positive, and their product is also positive. and the derivative of utility one of utility related to quantity 2 must be higher than equal than 0. The same. This time Q1, the quantity 1 is assumed to be constant. Quantity is right, so it's 1 minus alpha, quantity 1 at alpha, quantity 2 at minus alpha is higher than equal with 0. This is happening only if alpha is less than or equal with 1. That's why, as I said earlier, there are some constraints on the Cobb-Douglas function. So alpha cannot take any values. Alpha must be less than equal to 1. Now there are also certain conditions with the second derivative, and to implement the second derivative, we have this time, because we have two variables, we have to implement the Hessian matrix, of this utility function. So the matrix of the partial derivatives. So we just calculated the so the Hessian matrix delta 0 is 1, which is always positive. Delta 1 is minus the first term here, minus 1 alpha, 1 minus q1 at alpha mean minus 2, q2 at 1 minus, which is always positive because alpha is less than 1. Alpha 1 minus alpha is positive. Alpha minus 2 is negative. 1 minus alpha positive. Okay, and alpha is between 0 and 1. Delta 2 is also delta 2, which is determined by the determinant of this matrix. In order to calculate the determinant, the matrix has to be squared. So we have two rows and 2 columns. Yes, and we can calculate the determinant of this matrix. And we notice that the utility function is this Hessian matrix. This Hessian matrix is semi-definite, is negative definite. Okay, so now that we started that this is a utility function, the Cobb-Douglas function is known as being an utility function because we saw it satisfied the conditions. Now let's step B. Let's say let's formulate the optimization problem in this in our case. So we have to maximize utility being a function of quantity 1, quantity 2, which is quantity 1 at alpha minus quantity 2 at 1 minus alpha. Consider the budget constraint. We have two prices, two quantities. Price 1, quantity 1 plus price 2, quantity 2, less than equal than the revenue. Then we indicate the Lagrangian function. Lagrangian is quantity 1, quantity 2 revenue. Utility minus lambda price 1, quantity 1 plus price 2, quantity 2 minus revenue. Utility function, we know it. It is the Cobb-Douglas function. So it's quantity 1 at alpha minus quantity 2 at 1 minus alpha minus lambda multiplied by price 1, quantity 1 plus price 2, quantity 2 minus revenue. So we construct the Lagrangian function, which is a function of quantities and revenue. The next step are the optimization conditions. So the derivative of Lagrange related to quantity 1 is 0. This means quantity 2 is constant and quantity 1 is varying. So it's we remember the rules, the alpha quantity 1 alpha minus 1 multiplied by quantity 2 1 minus alpha minus lambda price 1 is 0. And if we move lambda price 1 on the right side with opposite sign, so it's alpha quantity 1 at alpha minus 1, quantity 2 at 1 minus alpha is equal with lambda price 1. And the derivative of Lagrange related to the second quantity is 0. 1 minus alpha, quantity 1 at alpha, quantity 2 minus alpha, minus lambda price 2. 1 minus alpha, quantity 1 at alpha, quantity 2 at minus alpha is lambda price 2. So this is the second equation. And the third one, the derivative of Lagrangian related to lambda is 0, gives us the budget constraint we already know. Price 1, quantity 1 plus price 2, quantity 2 is equal with revenue. The third relation. So we see here we have three equations, equation 1, equation 2, and equation 3, with three unknown variables. Optimal quantity, so quantity 1 star, quantity 2 star, and lambda. Now we can get rid of lambda by dividing the two, because this divide lambda price 1 divided by lambda price 2, we get rid of lambda. So we divide the second equation divided by the first one. So 1 minus alpha divided by alpha. Quantity 1 at alpha, quantity 1 alpha divided by quantity 1 at alpha minus 1 means quantity 1. So it's quantity 1 divided by quantity 2 is equal with price 2 divided by price 1, because there's no lambda. And we obtain this here, that quantity 1 is quantity 2 multiplied, it's quantity multiplied by price 2 divided by price 1 multiplied by alpha minus alpha divided by 1 minus alpha. And here we can substitute this. So instead of quantity 1, we write it as quantity 2 here. So alpha, instead of Okay, so we get that this let's say Marshallian function, Marshallian demand function, because the demand finds the function of quantity consumed. So the Marshallian demand function is a function of price one, price two revenue, which is revenue multiplied by 1 minus alpha divided by price 2. And the first Marshallian function is a function one function of price one, price two revenue is revenue multiplied by alpha divided by price one. So we just obtained the optimal quantities. Now, if we have some figures here for revenue, for prices, and for alpha, we could have easily determined the optimal quantities. Now, the third question, if we have here, the third question is to, so I haven't mentioned here, just explain it. So question one says, show that Cobb-Douglas function is an utility function. So this was the question. The second, calculate the optimal quantities. So Q1 star Q2 star. So in other words, the optimal, the Marshallian demand functions. So this was the second question. The second the second is to write the utility function in the optimal point, in the optimal write the optimal utility function, which means U of Q1 star, Q2 star. Okay. Price one, price two. Then show that the elasticities of show that the sum of elasticities of optimal demand functions is 0. And we calculate the elasticity of the Marshallian function 1 related to price 1. So it's the derivative of F1 related to price 1. We just calculate the optimal value here. Multiplied by price 1, F1 is minus 1. Is minus 1. Elasticity of function 1 related to price 2 is 0. Price 1, okay. Elasticity of, okay, 0. And the elasticity function 1 related to revenue is 1. Price 2. Elasticity of function 1, price 2. Okay. This question says that calculate how much the optimal demand function changes if price 1 increases by 10%, price 2 goes up by 10%, and revenue remains constant. So here we have the Marshallian demand function is F1, price 1, a price 2, and revenue. And the revenue. And revenue increases by 10% too. And we write again this function as an index because it's 1 plus percent. So index, we are 1 plus percentage evolution divided by 100. That's an index. So we write here F1, so the Marshallian demand function is 1.1 price 1, 1.1 price 2, 1.1 revenue is 1.1 alpha V divided by 1.1 price 1, because we know, so we know this function is this one. So it's alpha 1.1. Yes, we know this. So it's F1 is no, here it is. So it's F1 is revenue multiplied by alpha divided by price 1. Okay, so this one. So it's alpha V price 1 So it's F1 price 1. So the optimal quantity, the optimal quantity remains the same if all variables go up by 10%. So we have to provide some economic interpretation, and this is it. And another question is what happened to the optimal demand function. Show what happens. So show what happens to the optimal demand function if price 1 increases by 7%, price 2 by 7, up by 7%, and a revenue by 10%. And we know the demand function. F1 is V alpha price 1, and we just substitute 1.1 by alpha, V divided by 1.07 price 1. So if we divide those two, we see that the quantity demanded increases by 2.8%, and how it's 1.028 minus 1 is 0.002, or in percentage is plus 2.8%. Okay. Now let's write the proof that Cobb-Douglas function is an utility function. This was already done on page 7. So this was already done in page 7. Then the next question is to calculate the Hicksian, the optimal. So calculate the optimal quantities Q1 star, quantity 2 star, or the so-called Hicksian functions. The first step would be to write the optimization problem. So minimize, in our case, revenue, price 1, quantity 1 plus price 2, quantity 2. Considering a given level of utility, so utility as a function of Q, quantity 1, quantity 2, which is the same Douglas function. We used it in our previous exercise, which is quantity 1 at alpha multiplied by quantity 2 at 1 minus alpha is average of U, or a given level of U. The second step is to write the Lagrangian function, So the Lagrangian, which is a function of quantity 1, quantity, and lambda. So always the Lagrangian has one or more lambdas, which is price 1, quantity 1 plus price 2, quantity 2 plus lambda, and the difference utility, constantly my utility as a function of Q1, Q2. So it's a price 1 Q1 plus price 2 quantity 2 plus lambda multiplied by utility minus quantity 1 at alpha, quantity 2 at 1 minus alpha. We write the optimization. So write the optimization. The next is to write the optimization conditions. So those are the steps 1, 2, 3. Write the optimization conditions. The derivatives, derivatives have to be equal to 0. And that's what we are doing here. The derivative of Lagrangian related to quantity 1 is 0. So price 1 minus lambda alpha, quantity 1 at alpha minus 1, quantity 1 minus is 0. So lambda alpha, quantity 1 at alpha minus 1 multiplied by quantity 2 at 1 minus alpha is equal with price 1. Then the derivative of Lagrangian related to quantity 2 is 0. So price 2 minus lambda 1 minus alpha, quantity 1 at alpha, quantity of minus I is 0. So lambda multiplied by 1 minus alpha, quantity 1 alpha, quantity 2 minus alpha is price 2. So those are the conditions. And we see we divide equation 2 by equation 1 because this way we get rid of lambda. So it's 1 minus alpha, quantity 1 at alpha divided by quantity 1 at alpha minus 1 is quantity 1. We have here alpha, quantity 2 at minus alpha divided by quantity 2 at 1 minus alpha is quantity 2, and it's price 2, price 1. And for here we see that quantity 1 is equal with quantity 2 multiplied by price 2 divided by price 1, alpha divided by 1 minus alpha. And we replace quantity 1 in here, let's say for example, any of the two here in this relation. No, in this one, quantity 1 at alpha divided by quantity 2. Instead of quantity 2, we write the quantity 1. So quantity 2 star So the optimal demand, now you obtain the optimal demand function is the following. Quantity 2 star is the second H2 is a Hicksian demand for price 1, price 2, the utility function. So is the utility 1 minus alpha at alpha, alpha at alpha, price 1, yeah, price 2 at alpha. So quantity 2 star, and the same here, the optimal demand, the optimal demand function, quantity 1 star. Okay, and now we calculate here it shows that if we increase prices by the same amount, let's say by lambda, this does not impact the quantity demanded. So if both prices go up by lambda, the final amount consumed remains the same. Calculate the elasticities. Calculate the elasticities. Calculate the elasticities. Elasticities. Okay. Price 1. Okay. So, and we see here, I won't go into much detail because it's a far more difficult exercise. You'll take a look at home, and if you have problems, can tell me. Now let's move to exercise 3. So we have the utility function is of the utility exercise 3. So utility is a function of quantity, which is C, and the number of hours worked, L. In fact, so the utility is a function of quantity consumed, and free time, which is 1 minus number of hours worked. P means price. So price multiplied by quantity is the number of hours. W is the average, is the hourly payment. So prices. This is the budget. This is the budget constraint. So we have the utility function of quantity consumed and free time, spare time. And we have the budget. The first, what we are, so we have more variables this time. Write the optimization problem. So we have to maximize this utility function. Utility depends on quantity consumed and the spare time, considering this budget. So we have Marshallian we have to determine, we have to calculate the Marshallian demand functions. We have to calculate the Marshallian demand functions. The next step is to write the Lagrangian function. Write the Lagrangian function. Then write the optimization. So the Lagrangian natural logarithm of quantity plus natural logarithm of 1 minus L, number of hours, minus lambda, price multiplied by quantity minus number of hours, or multiplied by payments, productivity here. Write the optimization conditions. So the derivatives have to be equal to 0. So the derivative of Lagrangian function related to quantity is 0. So 1 minus, so if you write the 1 minus, so the natural logarithm of c, the derivative is 1 divided by c minus lambda price, because this is the derivative of natural 1 minus L is 0. Lambda price is 0, so 1 divided by price is lambda. The derivative of Lagrange related to L is 0. So it's 1 minus L plus lambda W, because minus lambda minus L is plus. So lambda W is 1 divided by 1 minus L. And the derivative of Lagrangian related to lambda is 0 is our budget constraint. Is price multiplied by quantity is LW. Again, we use the same algorithm. We divide, let's say, we divide equation 2 by equation 1, and we obtain the following. W divided by price W is the average payment divided by price is C quantity divided by 1 minus L number of hours worked. So L from here we obtain L is 1 minus price quantity divided by hourly payment. So from here, so L is this one minus yes, we know that LW, so and 1, so we get L is 0.5. So where do we get this? We know price quantity is LW, so price quantity is L is 1 minus price quantity divided by W multiplied by W. So price quantity is W minus price quantity so 2 price quantity is equal with the W. So from here, we know that price quantity is equal with LW, or L multiplied by 2 price quantity. So L is equal with price quantity divided by 2 multiplied by price quantity. So price quantity is 1 divided by 0.50. Is 0.50 in our case. Now we know L. L is known as 1 is 0.50. Now we can replace it in any of those. So we know that in our case, price quantity is W divided average hourly payment divided by 2. L is the as I said at the beginning, so we have to determine C. So C would be W divided by 2 price. So the quantity consumed would be this one. Average hourly payment divided by 2 price. Okay.